Hello everyone. If you're aiming to become a Databricks Certified Data Analyst Associate, you are in the right place. I have gone through the newly updated official syllabus, summarized the key topics in detail, and compiled a comprehensive study guide to help you approach this exam. Please note that this content represents my own efforts and is not affiliated with my employer. Generally, I create my own notes, so I thought why not share my notes here as well, right? So let's get started on the journey to help you become certified.
Databricks Certified Data Analyst Associate Section 1. Databricks SQL 1.1 Describe the key audience and side audiences for Databricks SQL primary audience, data analysts, by analysts, and data scientists who want to run SQL queries, build dashboards, and share insights. Side audiences, data engineers, may use Databricks SQL for quick data checks, test queries, or to support data analysts. Line of business stakeholders, decision makers, for example, product managers, marketing leads who need to view dashboards but typically do not write queries themselves. 1.2 Describe that a variety of users can view and run Databricks SQL dashboards as stakeholders. Dashboards in Databricks can be shared with users throughout an organization, from executives who want high-level overviews to technical teams that need deeper insights. Permission levels vary, viewer, editor, etc., ensuring data governance while still providing wide visibility. 1.3 Describe the benefits of using Databricks SQL for an Lakehouse platform. Data processing unified platform eliminates the need to move data between systems. Queries run directly on Lakehouse tables. Delta Lake scalability offers the ability to handle both small ad hoc queries and large-scale data processing. Performance and optimization, built-in Delta Lake optimizations, caching, and query acceleration. Collaboration, shared workspace for analysts, data engineers, and other team members. 1.4 Describe how to complete a basic Databricks SQL query. Steps to query. 1. Navigate to the SQL workspace, Databricks SQL. 2. Open the query editor and choose the appropriate SQL endpoint warehouse. 3. Write a query using standard ANSI SQL. For example, select asterisk from table underscore name limit 10. 4. Click Run to execute and view results. 1.5 Identify Databricks SQL queries as a place to write and run SQL code. Query editor, a dedicated interface within Databricks SQL where users write SQL commands. Versioning and history. Queries can be saved, version controlled, and revisited in query history. 1.6 Identify the information displayed in the schema browser from the query editor page. Schema browser helps users explore databases, tables, columns, and data types. Users can quickly reference table structures, supported data types, and relationships among tables. 1.7 Identify Databricks SQL dashboards as a place to display the results of multiple queries at once. A Databricks SQL dashboard can contain multiple visualizations, charts, tables, counters based on different SQL queries, use cases, cross-functional reporting, KPI tracking, and at-a-glance performance metrics. 1.8 Describe how to complete a basic Databricks SQL dashboard. Creating a dashboard. 1. Save a query with a visualization. 2. Click Add to Dashboard and either add to an existing dashboard or create a new one. 3. Arrange and size your visualizations for readability. 1.9 Describe how dashboards can be configured to automatically refresh. Auto refresh. From the dashboard settings, enable a refresh schedule, for example, 5 minutes, 1 hour. Refresh and warehouse costs. More frequent refresh equals higher resource utilization, so choose a schedule that balances timeliness versus cost. 1.10 Describe the purpose of Databricks SQL endpoints warehouses. SQL endpoints warehouses, compute clusters optimized for SQL workloads. Roll, execute queries, handle concurrency, and provide elasticity for analytics workloads. 1.11 Identify serverless Databricks SQL endpoint warehouses as a quick starting option. Serverless endpoints. Databricks manages the cluster infrastructure entirely, allowing near-instant startup times. Use cases, rapid development, minimal overhead for ad hoc analytics. 1.12 Describe the trade-off between cluster size and cost for Databricks SQL endpoints warehouses. Larger cluster, faster queries but higher cost. Smaller cluster, lower cost but may lead to slower queries or concurrency limits. 1.13 Identify Partner Connect as a tool for implementing simple integrations with a number of other data products. Partner Connect, a feature in Databricks that simplifies integration with popular third-party tools, for example, Fivetran, Rivery. Quick setup, wizards to configure connections without extensive DevOps overhead. 1.14 Describe how to connect Databricks SQL to ingestion tools like Fivetran within Partner Connect. Select Fivetran to automatically set up authentication and credential passing data ingestion pipelines that land data directly into Delta tables. 1.15 Identify the need to be set up with a partner to use it for Partner Connect. Partner Connect generally requires a valid account subscription with the third-party provider, proper Databricks permissions to configure and deploy the integration. 1.16 Identify small file upload as a solution for importing small text files like lookup tables and quick data integrations. Small file upload allows direct file uploads within the Databricks SQL interface for quick data exploration or small reference tables (CSVs). SN. Ideal use: quick prototypes, lookups, or small dimension tables. 1.17 Import from object storage using Databricks SQL object storage. For example, AWS S3, Azure Blob, GCS can be connected via standard connections. Allows bulk data ingestion directly into Delta Lake tables. 1.18 Identify that Databricks SQL can ingest directories of files. If the files are the same type, directory-based ingestion, multiple files within one directory can be treated as a single logical table if they share the same schema and format. For example, all CSVs or all Parquet. 1.19 Describe how to connect Databricks SQL to visualization tools like Tableau, Power BI, and Looker. JDBC/ODB connections. Databricks SQL endpoints can be accessed through standard data connectors for BI tools. Direct integration. Some tools offer native connectors for Databricks. For example, Power BI connector for Databricks. 1.20 Identify Databricks SQL as a complementary tool for BI partner tool workflows. End-to-end analytics. Use Databricks SQL for data processing and transformations. Feed results to BI tools for advanced visuals, storytelling, and distribution. 1.21 Describe Medallion architecture as a sequential data organization and pipeline system of progressively cleaner data. Medallion architecture: bronze, raw, unfiltered data; silver, cleaned, filtered, and possibly joined data; gold, aggregated or domain-specific data, ready for analytics. 1.22 Identify the gold layer as the most common layer for data analysts using Databricks SQL. Gold tables typically have business logic baked in, providing simplified data sets for BI and ad hoc queries. Analysts often query gold to avoid dealing with raw or partially cleaned data. 1.23 Describe the cautions and benefits of working with streaming data. Benefits: real-time insights, up-to-date dashboards, immediate anomaly detection. Cautions: higher complexity, potential for incomplete data if ingestion or transformations lag, managing late-arriving data events. 1.24 Identify that the Lakehouse allows the mixing of batch and streaming workloads. Delta Lake with structured streaming unifies streaming and batch processing on the same data, simplifying architecture and enabling near real-time analytics. Section 2, Data Management. 2.1 Describe Delta Lake as a tool for managing data files. Delta Lake is an open-source storage layer that brings ACID transactions, schema enforcement, and time travel to data lakes. Provides reliability, performance optimizations, and governance features. 2.2 Describe that Delta Lake manages table metadata. Table metadata includes schema definitions, partitioning info, version history, and transaction logs. This metadata underpins features like time travel and schema evolution. 2.3 Identify that Delta Lake tables maintain history for a period of time. Time travel. Delta Lake can retain previous versions of a table, allowing queries and rollbacks at past states. Retention. Configurable based on business needs. For example, Delta.Lake retention duration. 2.4 Describe the benefits of Delta Lake within the Lakehouse. ACID transactions. Ensures data integrity. Schema enforcement. Blocks or warns about mismatched schemas. Performance, optimized for columnar access, especially with Z ordering, partitioning. Data governance, centralized management of data and version control. 2.5 Describe persistence and scope of tables on Databricks Managed Tables. Databricks handles both data files and metadata. Dropping the table removes the data. Unmanaged tables, metadata is tracked by Databricks, but data files reside in an external location. Dropping the table leaves data intact. 2.6 Compare and contrast the behavior of managed and unmanaged tables. Managed, Databricks stores data in the default storage location. Easier to set up and maintain. Data is removed if the table is dropped. Unmanaged, you specify the file location. Data remains even after dropping the table. More flexible for external data governance patterns. 2.7 Identify whether a table is managed or unmanaged. Clues. If the DDL did not include a location clause and used the default database, it is likely managed. If location is specified, it's an unmanaged external table. 2.8 Explain how the location keyword changes the default location of database contents. Location in a create table or create database statement explicitly sets where the underlying data files are stored. This overrides the default Databricks managed storage path. 2.9 Use Databricks to create, use, and drop databases, tables, and views. Databases. Create database DB_name. Provide an MA space. Tables. Create table db_name.table_name. Contain actual data. Views. Create view. As select. Are saved queries referencing data from one or more tables. 2.10 Describe the persistence of data in a view and a temp view. Views, permanent objects stored in the Databricks metadata. Temp views exist only within the current session or until the cluster restarts. Do not persist beyond that. 2.11 Compare and contrast views and temp views. Views, stored in database metadata. Accessible by all users with permissions. Survive cluster restarts. Temp views, session scopes. Useful for intermediate or ad hoc calculations. Drop automatically when the session ends. 2.12 Explore, preview, and secure data using Data Explorer. Data Explorer, graphical user interface in Databricks for browsing and managing databases, tables, and permissions. Preview data, quick sample of table rows without writing a query. Secure, adjust user and group permissions, for example, read, write, ownership. 2.13 Use Databricks to create, drop, and rename tables. Syntax. Create table. Drop table db_name.table_name. Rename, alter table old_name rename to new_name. 2.14 Identify the table owner using Data Explorer. Table owner, the user or service principal who created the table or was assigned ownership. Displayed under permissions in Data Explorer. 2.15 Change access rights to a table using Data Explorer access control. Table owners can grant, revoke privileges, select, modify, own, granular permissions, manage at the table, schema, or catalog level. 2.16 Describe the responsibilities of a table owner. Governance, ensuring correct permissions and data compliance. Maintenance, vacuuming old versions, updating schema, managing performance. Data quality, maintaining accurate, timely data within the table. 2.17 Identify organization-specific considerations of P-Data. Personally identifiable information handling requires compliance with regulations. GDPR. CPA. Databricks tools, data masking, encryption, restricted access, and auditing. Best practices, secure data at rest and in transit, limit access to only those who need it. Section 3, SQL in the Lakehouse. 3.1 Identify a query that retrieves data from the database with specific conditions. Basic query example, select asterisk from sales_db.transactions where purchase_amount greater than 100 and region equals EMEA. Emphasizes the use of where clauses for filtering. 3.2 Identify the output of a select query. Select query output, a result set table of rows and columns, which can be displayed, further processed, or visualized in a dashboard. 3.3 Compare and contrast. Merge into, insert into, and copy into. Merge into. Use for upserts, insert, update, or delete records based on matching conditions. Common and slowly changing dimensions, SCD, or streaming merges. Insert into. Appends new rows to an existing table. Simplest way to add data to a table with matching schema. Copy into. Typically used to bulk load data from external sources, for example, CSV or Parquet in cloud storage, into a Delta table. Common in ingestion pipelines. 3.4 Simplify queries using subqueries. Subqueries allow reusing query logic or intermediate results. Example, select order underscore id from orders, where customer underscore id in. Select customer underscore id from customers, where region equals EU. 3.5 Compare and contrast different types of joins. Inner join returns rows that have matching keys in both tables. Left outer join returns all rows from the left table, plus matched rows from the right. Right outer join returns all rows from the right table, plus matched rows from the left. Full outer join returns all rows from both tables, matching where possible. Cross join Cartesian product of both tables. 3.6 Aggregate data to achieve a desired output. Common aggregate functions: sum, count, av, max, min. Group by used to group rows by one or more columns before applying the aggregate. 3.7 Manage nested data formats and sources within tables. Nested data, for example, syn columns, complex data types like structs, arrays, maps. Functions like explode, get underscore syn underscore object, or syn underscore parse, depending on environment, help flatten or parse nested fields. 3.8 Use cube and roll up to aggregate a data table. Cube generates all possible combinations of group by columns. Rollup generates hierarchical combinations from the most specific to the grand total. 3.9 Compare and contrast rollup and cube rollup, good for hierarchical aggregations. For example, country right arrow region right arrow total. Cube produces all combinations of columns, which can lead to more rows but offers a more complete breakdown. 3.10 Use windowing to aggregate timed data. Window functions aggregate or analyze data across a sliding window. Example, sum sales over partition by region order by date rows between 3 preceding and current row. 3.11 Identify a benefit of having ANSI SQL as the standard in the Lakehouse interoperability. Familiar syntax for BI tools and data professionals. Ease of migration, simple to port existing SQL queries and logic from other platforms. 3.12 Identify, access, and clean silver level data. Silver layer, clean but not fully curated, often used as intermediate data sets for transformation. Cleaning, removing duplicates, handling nulls, standardizing data types. 3.13 Utilize query history and caching to reduce development time and query latency. Query history allows rerunning previous queries, analyzing performance, versioning. Caching speeds up repeated queries by storing results or partial aggregates in memory. 3.14 Optimize performance using higher order Spark SQL functions. Higher order functions transform, filter, aggregate, explode. Use cases: complex transformations on arrays. Maps directly in SQL for improved speed and less overhead than multiple joins. 3.15 Create and apply UDFs in common scaling scenarios. User-defined functions. UDFs can handle specialized logic not covered by built-in functions. Best practices: keep UDFs small. Consider vectorized or built-in functions first for performance reasons. Section 4, Data Visualization and Dashboarding. 4.1 Create basic, schema-specific visualizations using Databricks SQL. Visualizations, table view, bar chart, line chart, pie chart, etc. Basic steps: run a query. Right arrow click visualization. Right arrow configure chart type, axes, and labels. 4.2 Identify which types of visualizations can be developed in Databricks SQL. Table, details, counter, pivot table, default textual result set. Details expand on a single row or record. Counter, single numeric value. KPIs. Pivot table, summaries aggregated by rows and columns. 4.3 Explain how visualization formatting changes the reception of a visualization. Clarity, proper labels, legends, and color choices improve comprehension. Storytelling, emphasizing trends or comparisons guides stakeholder focus. 4.4 Describe how to add visual appeal through formatting. Formatting options, color palettes, axis scaling, font size, data labels, interaction, adding tooltips, hover effects, or clickable drill downs can enhance user engagement. 4.5 Identify that customizable tables can be used as visualizations within Databricks SQL. Customizable tables adjust column ordering, rename fields, set highlight rules, or conditionally format cells to create more intuitive data tables. 4.6 Describe how different visualizations tell different stories. Line charts, trends over time, bar charts, comparisons across categories, pie charts, proportions of a whole, scatter plots, relationships between two metrics. 4.7 Create customized data visualizations to aid in data storytelling. Use advanced features like custom color gradients, multiple series overlays, annotated points. For example, highlight a specific day or event. 4.8 Create a dashboard using multiple existing visualizations from Databricks SQL queries. Steps 1. Create queries with desired visualizations. 2. Open or create a new dashboard. 3. Add each visualization to the dashboard. 4. Rearrange and resize as needed. 4.9 Describe how to change the colors of all of the visualizations in a dashboard. Dashboard theme styling. Use Databricks built-in color palette settings or override them in each visualization's settings. 4.10 Describe how query parameters change the output of underlying queries within a dashboard. Parameterization allows dashboards to be dynamic, letting end users input or select filters. Example, a parameter for region that applies to all queries in the dashboard. 4.11 Identify the behavior of a dashboard parameter. Global parameter. One parameter can feed multiple queries. Mandatory versus optional. Some parameters can be optional, changing the filtering logic. 4.12 Identify the use of the query-based drop-down list as a way to create a query parameter from the distinct output of a different query. Dynamic drop-down. The parameter values come from a query's result set. For example, distinct list of countries from a locations table. 4.13 Identify the method for sharing a dashboard with up-to-date results. Sharing methods. Sharing a direct link to the dashboard. Schedule refresh for up-to-date data. Export as a static report (PDF) if needed. 4.14 Describe the pros and cons of sharing dashboards in different ways. Direct link. Real-time data. Interactive. Requires Databricks account access. Export. Portable offline version, but static data. Embed. Integrate into intranet or portals. Must manage embedding tokens or authentication. 4.15 Identify that users without permission to all queries, databases, and endpoints can easily refresh a dashboard using the owner's credentials. Owner credentials can allow colleagues to see results of queries they do not have direct access to, but with careful governance to avoid unauthorized data exposure. 4.16 Describe how to configure a refresh schedule in dashboard settings. Define frequency, hourly, daily, custom intervals, and warehouse to use. 4.17 Identify what happens if a refresh rate is less than the warehouse's auto stop. If the warehouse automatically stops sooner than the refresh interval, a subsequent refresh triggers a warehouse restart, adding to latency. 4.18 Describe how to configure and troubleshoot a basic alerts triggered if a query result meets a condition. For example, sales less than target. Configuration. Set threshold values. Define alert recipients. Choose frequency. Every refresh or once daily. 4.19 Describe how notifications are sent when alerts are set up based on the configuration. Email or possibly other channels. Slack, Teams if integrated, with details on the alert condition and query results. Section 5. Analytics Applications. 5.1 Compare and contrast discrete and continuous statistics. Discrete data, countable, finite values. For example, number of sales, count of customers. Continuous data, measurable on a continuum. For example, revenue, temperatures, distances. 5.2 Describe descriptive statistics. Measures, mean, median, mode, variance, standard deviation. Used to summarize and understand datasets. Central tendency and spread. 5.3 Describe key moments of statistical distributions. Moments, mean, first moment, variance, second moment, skewness, third moment, kurtosis, fourth moment. Provide insight into shape and properties of a distribution. 5.4 Compare and contrast key statistical measures mean versus median. Mean can be skewed by outliers, while median is more robust to outliers. Standard deviation versus variance. Variance is the squared measure of spread. Standard deviation is the square root of variance, more interpretable in same units as data. 5.5 Describe data enhancement as a common analytics application. Data enhancement, adding derived columns, sorting addresses, or combining data from various sources to enrich existing data sets. 5.6 Enhance data in a common analytics application. Example, enrich transaction data with geo-coordinates or demographic info to better segment customers or markets. 5.7 Identify a scenario in which data enhancement would be beneficial. Use case, retail analytics. We're adding weather data to store sales can uncover correlations in foot traffic and weather patterns. 5.8 Describe the blending of data between two source applications. Data blending, combining related but separate data sources into a single data set. Techniques, SQL joins or union of data sets with standardized columns. 5.9 Identify a scenario in which data blending would be beneficial. Use case, merging CRM data, customer interactions with financial data, invoices, payments, to provide a holistic customer view. 5.10 Perform last mile ETL as project-specific data enhancement. Last mile ETL, final transformations to tailor data for a specific buy report or data science model. Examples, calculating final KPIs, normalizing values, pivoting data. Final tips for exam preparation. 1. Hands-on practice. Spend time in the Databricks SQL workspace. Create queries, dashboards, play with endpoints, and test data ingestion. 2. Review best practices. Understand Lakehouse architecture, especially Delta Lake features such as ACID transactions and time travel. 3. Dashboard and visualization. Practice building dashboards, scheduling refreshes, setting alerts, and exploring parameterized queries. 4. SQL mastery. Familiarize yourself with ANSI SQL syntax, especially joins, window functions, and advanced SQL features. Rollup, cube. 5. Security and governance. Learn table-level permissions, data masking, and basic compliance considerations. 6. Partner integrations. Know the basics of how to integrate Databricks with ingestion tools, for example, Fivetran, and BI tools, for example, Power BI, Tableau. 7. Performance tuning. Understand how caching, larger versus smaller clusters, and partitioning can affect performance and cost.
If you found this guide helpful, please share it and don't hesitate to let me know if you would like to see more content like this for other certifications. I have no plans for monetizing this channel, even in the future. I do it simply to help others, but hearing your feedback genuinely motivates me to keep going. Good luck on your journey to become a certified professional. Thank you.